for inviting me to speak at this conference. Yes, so my name is Elisabeth Schopf. I'm a researcher at the ATLAS experiment, and today I will be reporting on the Higgs results from ATLAS and CMS. I would like to start out with a very brief introduction on the standard model Higgs boson. So the whole point of having it is that it is a particle that is associated to the Higgs field, and the Higgs field is generating the masses of the standard model particles as they interact with it. According to the theory, the Higgs boson should have a spin of 0, a charge of 0, but its mass is a free parameter. So when it was discovered in 2012, the mass was measured at around 125 GeV. And so once we know this mass and we assume that only standard model couplings occur, this will fix all the predictions for interactions. Our most powerful tool to study the Higgs boson today is the Large Hadron Collider, which is colliding proton-protons at a center of mass energy of 13 TeV. Nevertheless, the production of a Higgs boson is rather rare, so only 1 in 1 billion collisions is producing a Higgs boson. Once it is produced, it will immediately decay, and so the CMS and ATLAS detector are both perfectly equipped to measure decay products and reconstruct the Higgs boson. Between 2015 and 2018, the so-called LHC Run-2, both experiments collected a massive amount of data, and we expect to find roughly 10 million Higgs bosons in this data set. So really, we are in an era where we are transitioning to precision measurements, and also this large data set enables a large amount of opportunities to search for beyond standard model effects in the Higgs sector. A very brief reminder of the main Higgs production channels at the LHC can be found on the left-hand side. So the largest cross-section is the so-called gluon-gluon fusion, where we have the two gluons just producing a single Higgs boson. And then with smaller cross-sections, we have the Higgs boson being produced in association with other particles, and the cross-section is decreasing as the mass of the associated particles is increasing. In terms of decay channels, the decay channel with the highest branching ratio is the decay into a pair of bottom quarks with almost 60%, followed by a pair of W bosons, 20%. Other channels such as ZZ and gamma gamma have much lower branching ratios, around 1%. On the bottom in green, I indicated for you which of these production and decay channels we have already observed. And for the green ones, also all sorts of combinations between production and decay have been probed. We also found recently evidence for rarer decays, which I will discuss in a minute, and we are still searching for other production and decay modes as well. There are still lots of things we would like to measure about the Higgs boson. I just put a summary plot for you on the right-hand side. So far, it seems that the coupling strength of a particle to the Higgs boson is proportional to its mass, so in line with the expectation that they actually gain their mass via the Higgs mechanism. But you can see the precision on the fermions is still small, and we also don't know a lot yet about lighter fermion generations. I cannot possibly talk about all the Higgs results, but I hope I will give you a good teaser of the most recent ones. I will start with the Higgs to ZZ and Higgs to gamma gamma decay channel. So these are channels with a very clean signature. So you can find on the top a decay into 2 muons and 2 electrons, and on the bottom into 2 photons. And you can really clearly see the signature in the detectors of these particles. So therefore, these channels also lend themselves perfectly to measure the Higgs boson mass, because we can fully reconstruct these final states and measure these particles with a very good energy resolution. As you can see on the bottom, the data distributions in both channels, we clearly see a peak at the Higgs boson mass. ATLAS has recently updated their Higgs to ZZ measurement with a full Run-2 data set, and the mass is still at around 125 GeV. And for CMS, we have a Run-1 plus 2016 data combination of the ZZ and gamma gamma channel. Again, the mass is measured at around 125 GeV. The precision of this measurement is around 2%, 2 per mil, with the statistical uncertainty still being the limiting factor here. Now moving to the rare decays, we recently found an evidence for the Higgs to muon decay, which has a very small branching ratio due to the small muon mass. And so to squeeze out the last bit of sensitivity, this measurement is performed in all major Higgs production channels. And you can see them in the plot here on the right. in the different colors as being probed by the CMS experiment. In blue, the highest sensitivity is coming from the VBF category, which is the distribution on the left-hand side, which is using a multivariate discriminator. And here in the rightmost bins, you can see in blue the Higgs 2 mu mu contribution. The observed significance is 3 sigma. So yes, so this is an evidence, and the measured signal strength mu is determined to be at 1.2. And within the errors, it's consistent with the standard model expectation of 1. So this is to date the channel with the highest sensitivity for second generation fermion couplings. Atlas is measuring this same decay with a significance of 2 sigma. Then also very recent, so from last month, is the evidence for the Higgs to 2 leptons plus a photon decay, which is specifically requiring the dilepton invariant mass to be below 30 GeV. So this means this channel is dominated by photon to 2 lepton conversions, as also shown in the example Feynman diagram here. And this nicely complements the CMS and Atlas measurements in the Higgs to Z gamma channel. Specifically, the dielectron plus photon signature is very challenging because for a significant fraction of the events, we do have the 2 electron showers overlapping in the electromagnetic calorimeter. So dedicated event reconstruction and categorization algorithms have been developed in order to distinguish these merged electron events from single electrons and photons in the calorimeter. You can see on the right-hand side in the data spectrum, also here we get this nice small bump at around 125 GeV. And the significance of this bump is 3.2 sigma. The measured signal strength is 1.5 plus minus 0.5. So again, consistent with the standard model expectation. And so this is one of these candidate events where you have the Higgs decaying to 2 muons and the photon, and you can really see in red here the muon tracks, how close together they are. Now moving on to differential distributions, I will highlight here the recent measurements in the Higgs to ZZ channel, but I should point out that also differential distributions are probed in the Higgs to gamma gamma and WW channels. Yes, and so we do these type of measurements because they probe higher order cross-section corrections. So one distribution that is particularly sensitive to these corrections is on the left-hand side, the number of jets, because of course additional quark radiation is produced by higher order diagrams. You can see in black the data points, and then in the different colors a comparison to various theory predictions. The sensitivity, especially at high jet multiplicities, is small due to statistical uncertainty. Another point doing this is that, of course, also the differential cross-sections could be changed from its expected distribution due to contributions, for example, in loops from new particles and new physics. And so one distribution particularly sensitive to this is the transverse momentum spectrum, which is shown here in the middle, and again, a comparison with various theory predictions. And then I also would like to highlight really that we are entering an era where we can also start double differential distributions, measuring those. So here just an example of the PT of the Higgs boson and the PT of the leading jet in the event. But of course, still we are statistically limited. So we really hope with more data, also the precision of these measurements will increase. If we cannot measure differential distributions, a tool that is becoming very popular is so-called simplified template cross-section measurements. These are quasi-differential cross-section measurements where we split the phase space of a certain Higgs production mode into discrete bins of Higgs kinematics. An example for the gluon fusion shown here on the right-hand side, where we have different PT bins and different also number of jet bins. And so we can then parameterize the expected standard model signal yield per bin as cross-section times branching ratio templates. So there's still some model dependence in these measurements, but of course it's much less model dependent than just measuring overall signal strengths. Another nice feature is that it lends itself to reinterpretation within frameworks that probe anomalous couplings, such as effective field theories. So here's just how the Lagrangian in such a theory would be parameterized. We are probing up to a dimension of 6, usually in Higgs physics, and you can see these additional coupling modifiers here. which would then change the STXS cross sections. And you can see the impact of these modifiers on the gluon fusion cross section in the different PT bins, and again showing you that really the high PT regime is very sensitive to beyond standard model modifications. This is the recent STXS combination by Atlas, combining measurements in the Higgs to gamma gamma, ZZ, and BB channel. We have really very good precision in the gluon fusion channels. We also do start to probe these high PT bins highlighted here, and also more rare production mode bins are added, such as TH production. For the VH production mode, which is here on the bottom, the bottom one is the one with the highest sensitivity. This is coming from the Higgs to BB measurements. And then this can be translated into constraints on the EFT coupling modifiers. And so we can see here for various combinations of those. So really for some of them, we can put very stringent limits on those. The most stringent ones we have from hadron collisions. But to be fair, we also do have very stringent limits from lab experiments. Moving on to Higgs to WW measurements. So these are also very new. This channel has a large branching ratio, but the final state can't be fully reconstructed since we do have neutrinos from the W decays, and we can only infer their presence via means of missing transverse energy. Nevertheless, also here precision is really increasing, and you can see the reconstructed transverse mass spectrum, and in red we nicely see the Higgs peak above the standard model background. So here are two measurements from CMS and Atlas. So due to also improved analysis techniques such as machine learning, we can start probing more challenging production modes such as VH production, shown on the left-hand side. So this measurement is observing a significance of 4.9 sigma compared to an expected significance of 2.7 sigma, and is also complemented by measuring in two different PT bins for the WH and ZH production mode in the STXS framework. And then on the right-hand side, the gluon fusion and BBF STXS measurement. And so here we can really see that in some bins we really have very good precision to date, and everything compatible with the standard model within errors. The Higgs to tau tau measurement, most recent one by CMS using the full run-2 dataset. Again, the challenge here is neutrinos in the final state. If we probe tau to hadron decays, we also do have the additional challenge to distinguish those type of decays from jets that originate from parton fragmentation. And you can see also here that the signal, again, in the left-hand side, the invariant di-tau mass, the signal in red, it is clearly visible above the background, but we can also see there is a large amount of background here. Nevertheless, the full run-2 dataset enables us to measure STXS bins in the gluon fusion and BBF production channels, and this is shown here, again, with especially at low PT, very good precision. The Higgs to tau tau channel also is sensitive to the CP structure of the Higgs boson. For standard model Higgs boson, we would expect it to be purely CP even. We have excluded purely CP odd Higgs bosons, but there might still be an admixture of the two contributions. So what is done here, the mixing angle is measured, and it's measured at 4 ± 36 degrees. And so this is well compatible with the standard model expectation of a mixing angle of 0. Now moving on to Higgs boson decays and productions as well that result in final state with jets. There are two challenges here. The first challenge is that it's very important to be able to identify B jets, so originating from bottom quark hadronization. This is important for the TTH production channel and also for the Higgs to BB decay channel. We can do this because the secondary vertices of the B hadron decay can on average be reconstructed, and we can also measure the track impact parameter. And if we put all of this information in a multivariate algorithm, this can provide us with a rather efficient B jet identification, and this is the case in Atlas and CMS. So yeah, so for one channel where this is important here, just as an example, a TTH diphoton event, you can also see it's a very crowded event. So really lots of work to do in terms of reconstruction. Then when we move to higher and higher transverse momenta, we get the two B jets of a Higgs to BB decay being closer together and at some point overlapping in the hadron calorimeter. So we cannot disentangle them any longer. So what we do instead is we reconstruct the Higgs candidate as a single large radius jet with a two-prong substructure. Here the Higgs to BB measurements. So this is the channel, as I mentioned before, with the highest branching ratio of 60%, but it is very challenging since the jets in final states in proton-proton collisions are really very abundant. So it's very difficult to find the few Higgs bosons events amongst the large amount of multi-jet events that we have. So this is why the highest sensitivity in this channel we can actually reach in the VH production mode, since we get several orders of magnitude of background suppression from the V2 lepton decays. And so here I put two examples of the invariant mass spectrum of the two B jets in the VBF production channel. So this is a fully hadronic channel having the challenge of this large amount of multi-jet background. But nevertheless, we can see here this small bump at around 125 GeV, and the significance of this bump is 2.9 sigma. And then for the VH channel, we have a clearer bump, and actually the WH channel is measured with a significance of 4 sigma and the ZH with 5.3 sigma. But I also want to highlight here that the jet energy resolution really is much worse than, for example, for leptons. Maybe you remember from earlier for the 4-lepton channel where we nicely could separate the Z peak and the Higgs peak. Here we really have them merging together. The good precision of the VH channel allows us to perform the SDXS measurement. So this is the one that entered the combination I've shown earlier. And we can really see the good precision that we have, especially in the higher PT regimes, and also how nicely it's compatible with the standard model expectation in these bins. If we want to probe very high PT, we can also do this in the Higgs to BB channel. So Vera production decay channels have the disadvantage that there's not enough data statistics at high PT. So here the high branching ratio is the selling point for the Higgs BB channel. And in order to go to very high PT, we just probe inclusive Higgs production. So these are fully hadronic final states. And you can see here on the left-hand side, the invariant mass spectrum of the CMS measurement in the regime of around 1 TeV. And so still here, we expect really a handful of Higgs boson decays. And so this is then translated in a differential measurement shown here on the top in the middle. And a similar measurement is also recently published by Atlas. And so we really can go up to a few TeV, but still the statistical uncertainties in this high PT bins are large. So the best sensitivity we still get from the VH channel. And so this is the boosted VHBB measurement by Atlas. So all measurements shown here are reconstructing the Higgs boson candidate as the single large radius jet. So here we can add this additional bin at above 400 GeV, but the low production times cross-section for these channels doesn't allow us to go here to up to 1 TeV as we can in the inclusive measurements. The coupling of Higgs boson to the standard model particle with the highest mass can only be probed in associated production, so TTH production. And here the challenge is that the cross-section of this production mode is rather small. As we have seen in the event display earlier, we do have many final state particles, so also lots of combinatorics going on. But nevertheless, I want to highlight the good precision we can now reach in these states. Here, the recent measurement of CMS in the multi-lepton final state probing Higgs to WW, ZZ, and tau-tau decays. The significance here is 4.7 sigma. The measured signal strength 0.9 plus minus 0.3 roughly. Another challenge is that the backgrounds in the TTH channels often come with large theory uncertainties. So here more specifically the STXS TTH-BB measurement, the largest limitation is the uncertainty on the prediction of the TT plus BB process. And then another
Elisabeth, 5 minutes.
Okay, thank you.
Yeah.
Yes, and then another measurement we can also do in the TTH production channel is to probe the CP structure, so complementing the Higgs to tau measurement. And also here we can set upper limit on the mixing angle, and these are very comparable with what we've seen from the tau measurement before. Now I would like to move on to di-Higgs production. So this is a very interesting process because it gives us direct access to the Higgs self-coupling strengths. As shown here in the Feynman diagram, we get this triple Higgs vertex. And so this probes the shape of the Higgs potential. So of course, the production of a single Higgs boson already is a rare process. So of 2 Higgs bosons, it's even rarer. So we expect this to reach full potential at the high luminosity LHC. Nevertheless, of course, we can try to do the best we can with the data set we have. And given the limited data statistics, we have to find a good compromise between probing decay channels with high resolution, such as gamma-gamma, and decay channels with a reasonably high branching ratio. So most of the searches are performed in channels with BB plus something else. If we probe very specific production modes, such as BBF shown here on the bottom, we can also probe the HHVV vertex, which is also a very nice feature. I will only highlight one channel, which is the BB gamma-gamma channel, which currently has the highest sensitivity to standard model di-Higgs production. And here large improvements also to the sensitivity have been made for the full run-2 analysis using machine learning. The photon invariant mass here on the left and the di-B-jet mass on the right, we don't see any fluctuations over the background, but nevertheless we can set limits on the cross-section times branching ratio for the standard model di-Higgs production. In addition, also both analyses are performing a scan over the full mass range for potential di-Higgs resonances. Here are the results of the standard model measurement. So the cross-section times branching ratio limit set by CMS at a 95% confidence level is 7.7 times the standard model expectation, and Atlas is setting the limit at 4.1 times the standard model expectation. So really impressive limits here. Then also the triple Higgs coupling strengths is limits are set on it. And then the CMS analysis has a dedicated VBF category, also probing this HHVV coupling strength parameter. In Atlas, this is done in a VBF di-Higgs to 4B analysis. The last few minutes I want to spend on beyond standard model searches. So the first one of those is searching for a heavy Higgs boson that is in turn, for example, decaying in additional Higgs bosons. So this is really probing extended Higgs sector theories. The latest measurement by CMS in the tau-tau-BB channel is shown here, and 95% confidence level exclusion limits are sent over large mass range going from a few hundred GeV up to TeV, and the most stringent limits are set on high mass scenarios. Then this can also be reinterpreted in a very specific model here for the next to minimal supersymmetric model. And the blue contour here is showing you what type of masses are not excluded yet in this scenario. Atlas has a similar measurement searching for heavy Higgs boson A decaying to ZH. And then again, large mass ranges are probed with the most stringent limits setting at high masses. We can also search for heavy Higgs bosons that are charged, again, also part of several extended Higgs sector BSM models. CMS recently has probed singly charged and also doubly charged Higgs bosons in the case into vector bosons. And again, large mass ranges are probed and very stringent limits are set. And then here on the right-hand side, I show you one Atlas measurement probing a positively charged Higgs boson decaying into a top plus a bottom quark. And again, you see the very stringent limits on a large mass range. We can also use the standard model Higgs boson. So here now, this is the 125 GeV standard model Higgs boson, but now probing new particles in the final states. So assuming that these new undiscovered particles would also gain their mass via the Higgs mechanism. On the left-hand side, the most recent measurement by Atlas, Higgs decaying to 2 spin-0 particles in the BB mu channel. So here we are really probing lower masses, so several 10 GeVs. And there's just one axis being found with a global significance of 1.7 sigma. Of course, many more decay channels are probed, and a summary of the maximum allowed branching ratios of these type of decays are shown here on the bottom. I want to highlight one specifically, which is Higgs to dark matter decays. So again, assuming dark matter is getting their mass via Higgs mechanism. And of course, we couldn't detect dark matter particles with our detector, so we would just find missing energy in the final states. And Atlas recently has combined several measurements of run 1 and run 2 into an upper limit of the branching ratio Higgs to invisible at around 11%. CMS has a run 2 ZH measurement where the limit is set at 25%. And so, yeah, so this is my summary. So really the LHC run 2 data sets enabled Atlas and CMS to perform standard model measurements at unprecedented precision. A vast program of BSM searches is performed. So far, everything is consistent with the standard model, but of course, we expect much more data to come during LHC run 3 and also the high-LUMI LHC operations. So yeah, so I think we can all be excited for more Higgs results, and thank you for your attention.
Okay, thank you very much for a very interesting and comprehensive talk, Elisabeth. I invite questions. This is done by going to the menu at the bottom and clicking on the reactions tab. You can see raise hand there if you're not used to it. Or, well, okay, I think Aaron was first.
Indeed, a beautiful talk, Elisabeth. On slide 7, you showed a very nice, it's always nice to see the Higgs in this four lepton distribution of which Atlas you presented here. Now, Emanuela told us and showed us measurements of double parton scattering when you have a 4-body final state. I don't see here in any of the backgrounds which is shown double DPS. Has anybody measured DPS in 4 leptons at LHC?
Oh, this I honestly don't know. I'm maybe not the right person to answer this question.
Okay.
Yeah, well, if any of the audience can answer it, please put it into the chat. But I think the next person to ask a question is Paul.
Thank you. So you showed us first evidence for Higgs to muon decays. Is that all we can hope for from the LHC in terms of first and second generation couplings, or can we still hope for Higgs to charm, for example?
So Higgs to charm is yes, it's a tricky business. I think for the muons, of course, with more statistics during LHC run 3 also we can. Yeah, I think for the muons, there's lots of hope, and then especially in the high-LUMI scenario. For the Higgs to charm, I do have I think a slide in the backup. So this is much more challenging since we cannot very effectively identify charm jets with the detectors that we have. Yes, so this is the slide here. So we do have results from Atlas and CMS with the partial run 2 data set using the 2016 data. And you can see the upper limits being put here. Atlas 110 times standard model expectation in just the ZH channel, and CMS has also more production channels. And I think the upper limit is set at around 70 times the standard model expectation. So, and I think there exist high-LUMI extrapolations At least the Atlas one of this analysis I'm aware of, this is setting the limit for 3000 inverse femtobarn at around 5 times the standard model expectation.
Okay. Anybody else with a question? If we can suggest, we've already noticed that people seem to be a bit reluctant to ask questions. Another way to do it would be to type it into the chat box, and we can look at that, you know, type it in as the talk is going along even, and we can look at the questions, and I could read them out if that's what's inhibiting you, but I really can't see any more right now. So I think we should just thank Elisabeth again, and and move on to the next talk, which is about the spin structure of the nucleus. So Carolyn, yes, already sharing.
Hello.
Thank you. Hello.
Yeah.
Yes.
Hello.
Hello. Yes.
Okay. That should be full screen now.
Full screen.
So
yes. That looks great. So well, I'll give you a warning after 20 minutes. Okay.
Okay. Thank you
And
very
please,
much. And
please go right ahead.
Yeah. Thank you for the opportunity to speak here today about recent highlights from spin physics experiments. And I wish I could all meet with you in person. So in my talk, I will show experimental results from various facilities from BNL, Fermilab, Jefferson Lab, DESY, and CERN. And I won't have time to cover all the details of the experimental setup and the analysis, so I refer to the parallel sessions for everything. So so the physics questions of my talk are going to be the following. So how do quarks and gluons and their dynamics make up the proton spin? So this is commonly known as the spin puzzle. So how is the proton spin decomposed from the spin of the quarks and the orbital angular momenta and the spin of the gluons? And secondly, not unrelated, the three-dimensional structure of the proton on the one hand side in transverse momentum space with the so-called transverse momentum dependent PDF or TMDs, and on the other hand, in position space, the generalized parton distributions or GPDs. And since this is a DIS conference, I'm not really going to introduce a DIS, but I want to remind you that in semi-inclusive deep inelastic scattering, where one or more hadrons are detected, we also gain information about the transverse intrinsic momentum of the struck parton. And so I jump right into the parametrization of the CIDIS cross-section that can be broken down in pieces containing products or convolutions of PDFs and fragmentation functions. And the experimental access to each of these building blocks is obtained by measuring the amplitude of the azimuthal modulation with respect to a certain combination of the azimuthal angles phi s and phi, as shown here. So we typically access spin asymmetries in our experiments. And so what are all these different functions here written out? Why are there so many and what do they mean? So they can be grouped in a table of TMD functions grouped by the polarization of the nucleon that can be unpolarized longitudinally or transversely polarized, and as well the same for the quark, so shown here as the rows of the table. In the main diagonal, you find elements that survive integration over the transverse momentum, so-called collinear analysis, while in the off-diagonal elements, you find TMDs that describe the strength of spin-orbit correlations, and you also find chiral odd TMDs. And as we go along through the talk, I'm going to show you the measurements. So the first one I want to show you is the TMD effects in unpolarized CIDIS. And here there are two new preliminary results, one being from COMPASS, showing the PT dependence, and the other one, the class 12 pion multiplicity. So as is usual nowadays, these analyses are done in multi-dimensional bindings and various kinematic variables. This allows to perform TMD evolution studies and also a comparison between experiments. These new data will help to address one of the points, namely the double Gaussian structures found in the transverse momentum distribution, and also investigating why the real KT square of previous fits was underestimated. And the data will allow towards a more complete mapping of the CITES landscape, investigating current and target fragmentation. This is also performed by using, for example, the QT parameter as shown here in the compass plot, which allows to validate the region of the TMD formalism. Next, I come, even so it's not spin dependent, to important new results, the flavor composition of the C. This has already been flashed by Cynthia, the new sequest E bar over U bar result obtained in Brilliant scattering at Fermilab. And also there's a new result from STAR in a weak boson production showing the cross-section ratios of W plus over W minus. So we clearly see there's a flavor asymmetric C. The D bar is larger than the U bar. And so these two measurements are complementary to each other and also to the results from the Large Hadron Collider. So the same process, but in W plus and W minus production, but this time using longitudinally polarized beams, is used at STAR and Phoenix to learn something about the quark helicities. And the results of this are shown here. There's a strong evidence for flavor symmetry breaking in this polarized sector that is, however, opposite to the unpolarized sector. There's also a final result from Hermes on CITES valence quark distributions showing here obtained in the charge difference double spin ALL symmetry. Next, moving on to the helicity of the gluon. And again, we stay at RIC with the collision of longitudinally polarized beams. At RIC, it is possible to directly access the gluon helicities because the quark glue and glue processes dominate. And I want to point out results from Phoenix and charged pion production, the double longitudinal symmetry shown here, and also with recent results from STAR in dijet and inclusive jet production. These results are at very high precision and mid rapidity. They are consistent with the existing global QCD fits that indicate a non-zero, positive and large 60% gluon spin contribution to the proton spin in this probe region of X Bjorken. Next, I move on to spin orbit correlations in the proton. And if certain TMDs are determined to be non-zero, this is indicative of parton orbital angular momentum in the proton, even though there's not really a quantitative relation yet between TMDs and this orbital angular momentum. The Sivers effect describes the correlation between the transverse spin of the nucleon and the parton transverse momentum in the polarized nucleon, while the so-called Collins effect describes the fragmentation of a transversely polarized parton into a final hadron. So originally, this Sivers function was thought to vanish, but then it was realized if QCD final state interactions are included, that the Sivers effect can be non-zero. And I want to show you next the results from Sivers asymmetries obtained in CITES. Here showing the final Hermes Sivers asymmetries from a recent final compendium of Hermes TMD results that was done with a refined analysis, again in multidimensional binning. Here it is shown that the kaon amplitudes are larger than those of the pion, which may point to a role of the C quarks. Also, the first results on proton and antiproton are shown here. The Sivers asymmetry was also measured at COMPASS in CITES, and here showing the result from the so-called PT-weighted symmetries. It is directly possible to access the the Sivers function, and here are shown the Sivers asymmetry for U and for D quarks, and they have opposite sign. This is a very well known result. And also I want to mention that the Sivers signal at compass is smaller than that at Hermes. This is usually attributed due to TMD evolution and the larger beam energy at compass. So CIDIS is not the only process that can probe TMDs. There are other processes such as Drell-Yan and WC production, electron-positron annihilation, and proton-proton collisions. And by measuring TMD observables with all of these different scattering processes allows us to probe TMD universality. And there's one in particular important experimental prediction, namely that the naive time reversal odd TMDs, the Sivers and the Bohr-Mulder function switch sign when measured in CIDIS with respect to measured in Drell-Yan. And this is because when you have final state interaction in CIDIS, you have initial state interactions in Drell-Yan. And this experimental test of the sign switch is a very important test of the TMD framework. And there are two collaborations that have addressed this experimentally. One of them being COMPASS, that measured the Sivers asymmetry also in Drell-Yan scattering using a negative pion beam on a transversely polarized proton target. The result of part of the data is shown here in comparison with the CIDIS world data, also including the COMPASS data. And so COMPASS has measured the Sivers asymmetries in the overlapping kinematic range and with the same apparatus. So this measurement indicates that the sign switch is favored from the Drell-Yan measurement. There is also possible to extract other TMDs from these data, such as Pratt's velocity and transversity, and in particular the Bohr-Mulder's function. There will be a talk later in this conference also showing the Lam-Tung relation on tungsten, and this will be the first showing of that in public. There is more data on tape. The STAR experiment has measured a transverse spin asymmetry in W plus minus production shown here. Also, these data favor the sign switch of the Sivers function. And also STAR is currently analyzing more data. So the experimental data tend to support the sign switch, but the experimental uncertainties are rather large at the moment. So the this STAR asymmetry I've shown you on the previous page is an example of a so-called left-right or A sub n asymmetries, which has been measured over the past few decades in hadron-hadron collisions over many orders of magnitude of square root of S, and has been found to be independent of that, and with quite significant rise towards X-Feynman. And there has been a lot of theoretical work ongoing in the recent years to try to explain this existence of the left-right asymmetry across all the different collision species. And on the one hand side, we have in the collinear twist-3 factorization a one-scale problem with one hard scale, where the A sub n is accessed in a single inclusive particle production. On the other hand, we have the TMD mechanism that requires two scales, one hard and one soft, where the A sub n is accessed in CIDIS, Drell-Yan, WC, Dietzsch, or hadron and Chet production. So it is important to continue the measurement to further the understanding of the origin of this A sub n. And so let's look at some recent results from Phoenix. Here accessing the twist-3 trigluon correlation function that is related to the gluon-Sivers function. And here Phoenix has recent results on the A sub n in direct photon production, which is a very clean probe, and also on pi and eta production. And I want to point out that the contribution of gluons is expected to be largest at the small pt, as shown here in the process dependencies. And so when you look at the data, it's that even so the data are at very high precision, they're not really signals visible. And the question is now, or one can ask the question, how do these results relate to the non-zero results from COMPASS obtained in CIDIS? There is a result from photon-gluon fusion and exclusive psi lepton production. Therefore, it's interesting to look also at the Sivers asymmetry in shape psi production in pion-proton collisions at COMPASS. The results will come later. Now moving to the very forward, there the situation changes. So looking at very forward ASAP-N has been very fashionable recently. There are results from Phoenix detecting very forward neutrons using a 0-degree colorimeter shown here in the left plot. Then there's a recent result from the RIG forward collaboration using using also a colorimeter away from the star interaction point, and then also pi-0 and electromagnetic jets at star using a forward Meson spectrometer. So here ASAP-N increases with transverse momentum, forwardness, pi-0 isolation, and the multiplicity of the photons. And this may point to ASAP-N coming from soft processes such as diffractive scattering. I now move to the Collins asymmetries that turn up in the cross-section as a convolution with transversity. TMD here showing results of the Collins asymmetry from star by hadrons and jets for positive and for negative pions, showing a different sign of that asymmetry. Also, there's another fragmentation function, the dihadron interference fragmentation function, where two pions are measured, and the result from star here is shown in this bottom right plot. So these RIG results enable a test of TMD universality and factorization breaking. And then moving on to the Collins asymmetries in CIDIS, here I remind of, again, showing results from the Hermes compendium, the Collins asymmetries for positive and negative pions, where you see the mirror symmetry for the two pion charges. This is related to the opposite signs for favored and unfavored Collins fragmentation functions. So all of these data are taken and in global fits, global extractions, and you see here the example of the Collins fragmentation function from the previously mentioned CHAM 20 from the CHAM collaboration, and also showing the global extractions for the transversity TMDs, and they're also curved from other collaborations. So you see, looking at the transversity fits, that the uncertainty for the d-quark transversity is significantly larger. And therefore, it will be very important that COMPASS this year will have another transversity run on a transversely polarized deuteron target that will double the experimental precision on the proton's tensor charge, which is the difference between U and d quark transversity. Before moving on, I want to point out that there's also experimental access to other spin-dependent fragmentation functions. There is COMPASS data on a transversely polarized target that that is sensitive to the fragmentation function, describing fragmentation of quarks into vector mesons. And here it will be interesting to investigate the Collins mechanism of spin 1 vector mesons versus that of the ordinary Collins fragmentation function of pseudoscalar mesons. The results will be shown later at this conference. And class 12 investigated a beam spin asymmetry in dihadron production that is sensitive to the helicity-dependent dipion fragmentation function. The results are shown here, and there's also a related result from class that also is sensitive to higher twist TMDs. And higher twist is also a very fashionable topic at the moment. There are results from class 12 and Hermes on CIDIS beam spin asymmetries. that are sensitive to higher twist TMDs, and for example, the TMDE appearing here. And in this plot is compared the class 12 measurements with previous measurements from class, but also from Hermes and from COMPASS, and this provides information about quark-gluon correlations in the proton and in the hadronization process. GPDs, now changing subject, can be accessed by hard exclusive processes that were also mentioned by Charlotte before. If a real single photon is produced, we speak of deeply virtual Compton scattering. If a vector or pseudoscalar meson is produced, we call it deeply virtual meson production. And there has been, over the past 20 years, a multitude of measurements at Hermes, JLab 6 and HERA, to nowadays COMPASS and JLab 12 and also RIG, and shown in this X-Q² coverage here. So there are, to mention that, 4 chiral even and 4 chiral odd GPDs. And let's see what the recent measurements are. So the first one I want to talk about is the transverse imaging of the nucleon, looking at the differential DVCS cross-section with respect to the squared momentum transfer. We see that it falls exponentially with the B slope, or the average impact parameter. So at COMPASS, we can
Caroline,
access the...
you have 5 minutes, okay?
Yes, thank you.
5 minutes, thank you.
Thank you. At COMPASS, we can extract a pure DVCS cross-section because due to the low reach in X, we can extract at lower X, so-called Bethe-Heitler reference yield, where Bethe-Heitler is a process with the same initial and final state, so it also appears in the single photon events. By doing so, we can determine the transverse extension of partons inside the proton, and the result of the B slope of the COMPASS data is shown here in the red data point at higher values of X-Bjorken than probed previously by the H1 and SUS collider experiments. These data is from the 2012 data. There are about 10 times more data on tape, and from the new data, so more to be expected. The GPDs experimentally are accessed by performing measurements with Compton form factors, and here it is advantageous to probe as many experimental configurations as possible by changing target polarization, beam polarization, and beam charges. So, for example, this will also be done at COMPASS to access real and imaginary part of the DVCS amplitude, so to basically scan the entire region of the, or as much as possible, of the Compton form factors. At Hall A on neutron DVCS, this has been done here, shown the plot for showing real and imaginary parts of different Compton form factors. Also, by performing a flavor separation of for U and for D quarks. Looking at the dispersion relation for DVCS, there is a D term that is related to shear forces and radial distribution of pressure inside the nucleon, and here class and class 12 can significantly improve our knowledge about this distribution. This will also be in particular interesting to look at time-like Compton scattering at class 12, as is currently being done. The GPTE is linked to orbital angular momentum via the G-sum rule for the nucleon. There are some recent data have been taken at class 12, and there will be more data taken on a transversely polarized proton. And so all the GPDs we discussed so far were quark GPDs. There is one new measurement by STAR in exclusive J-psi production, also mentioned by Charlotte, in ultra-peripheral collisions that is sensitive to the gluon GPDE, the very preliminary result shown here. And there will be significantly more data taken for that channel after the forward upgrade of STAR. So we are now going so this allows to probe C quarks and gluons by involving COMPASS and STAR data. The chiral odd GPDs HT and ET can be accessed in the exclusive pi0 cross-section. It's done by COMPASS. The results shown here. There is also the analysis ongoing at class 12 for exclusive pi0 and the beam spin asymmetry, and for exclusive pi plus that is more sensitive to HT and will improve that that access. Spin density matrix elements describe how the spin components of the virtual photon are transferred to the created vector mesons, and they can be extracted by making use of the self-analyzing characteristics of the vector meson, and by performing an angular analysis of the cross section. And I want to flash here the new result published of the COMPASS STMEs, shown here all the different transitions. And I want to point out a transition in class C that shows a significant violation of S-channel helicity conservation, and also with an interesting kinematic dependence. And this transition is sensitive to the HT and ET GPDs. One can then also look at the cross-section ratio R of longitudinal to transverse vector mesons, and shown here for omega STMEs. And there's also a new preliminary result of for rho STMEs that will be shown later at this conference. And one can make a comparison to Hermes, who has also performed these measurements. Some more selected measurements I found interesting. That class has a first true signal of coherent DVCS on helium. And this was done by detecting the helium recoil and seeing for the first time a DVCS amplitude that is larger than that on the proton, which may point to a generalized EMC effect. And previously at Hermes, because the recoil was not detected for the nuclear data, this was not really observed before. There's also in exclusive pi plus production a beam spin asymmetry in the backward that allows to study nucleon to pion baryonic transition distribution amplitudes, or TDAs, which are a further generalization of the GPD concept. And that brings me to the slide about the near future. So in addition to the COMPASS 2021 run this year, there is the ongoing program at Jefferson Lab 12, the high luminosity facility. There will be cold QCD runs with STAR with the forward upgrade. There will be a cold QCD run with S-Phoenix in 2024. And SpinQuest will perform the first polarized Rayleigh experiment with a proton beam to access C quarks. And then there will be the AMBER experiment, basically being the follow-up experiment of COMPASS, and then further facilities and wherever TMD studies and related studies and GPD studies will be possible. So this brings me to the summary. I've shown you recent results from experiments at various facilities that are sensitive to the spin and multidimensional structure of the proton. So we know nowadays that the spins of quarks and gluons contribute to the proton spin, and there is indication that there's also orbital angular momentum of partons inside the nucleon. The nucleon is explored by tomographic images in TMD space and in position space. And I just include some of the more recent extractions from Barchetta et al. And from for the TMD, and from Motard et al. In the position space that really allow almost breathtaking images of the nucleon. And of course, with the electron-ion collider, we will have the ultimate tool to very precisely map the nucleon. Thank you.
Thank you very much for, again, a very complete review of the experimental results on spin. So I invite questions. Don't see any in the chat, I don't think. Giving you a few minutes to put your hands up. Oh, I see that Abe has put his hand up.
Caroline, thank you very much for this nice review. You said Amber phase 1 has been approved. Maybe you mentioned but went too fast. What part of the physics will be done in that phase 1? What all
This will be with the conventional hard-on beams at the M2 beam line. So,
okay.
Also with muon beam, this is still possible. This will be before the RF separated upgrade. So starting with a proton radius measurement and yeah, basically pion structure.
Great, thank you.
And Pavel?
Yeah, I just wanted to comment on the remark that while we see substantial evidence for the d bar minus u bar asymmetry in the spin case, we do not see it in the unpolarized case. I believe we need to be very careful because the conclusion that very strongly depend on how uncertainties are treated. And so therefore, I would, like, for example, you showed that the CT-ATN uncertainty agrees very well with the case when d bar over u bar is equal to 1, but it also allows some non-zero value of this ratio. And I believe it's the same situation in the polarized case. So then how do we understand the uncertainties for these measurements so that we can make physics conclusions like what you just presented?
Yeah, okay, thank you for that remark.
Okay, if I just pose a question myself as a person who is an expert on spin, and we've been hearing about the spin crisis now for many years, and now we know, of course, it's not all taken by quarks, it's taken by quarks and gluons. There might be some angular momentum, but we still don't seem to have a very complete picture of how much is taken by what. And how long do you think it would take before we could get such answers?
Well, certainly we will not be able to have a full picture before, and not a lot of EIC data will be analyzed. So it will be well into the 2030s. And I wouldn't call it a spin crisis anymore. It's more like putting it together. So we know that a bit less than a third comes from the spin of the quarks. We have a pretty good idea now about a gluon spin in this X region at least. So I mean, you need to go to more precision data at some lower X, and let's say probably by, I don't know, by 2040, we'll know
Okay.
maybe a complete picture.
Yes, yeah. Okay, now there is a question come in, Gunnar Schnell.
Yeah, hi, Caro. Gunnar.
Hi.
You mentioned for the Sievers gluon effect that there's a measurement by compass for exclusive chip type, but shouldn't we understand that data much more in the framework of GPDs and not in terms of the Sievers function? Because it's exclusive chip type production on transversely polarized target?
Yeah.
I know it is often mentioned in that,
Yeah.
but I never understood. And so maybe.
Yeah. I don't have an answer out of the box, but I would like to discuss this. Maybe we could take it together, Town. I have to quickly think about it. Okay. Maybe someone wants to chip in.
Okay.
I mean, it is a it is a measurement at very high Z. Yeah. So it's not. I mean, it is quasi exclusive. But, yeah.
Because later in the talk, you also mentioned the same process, or almost the same process in ultra conditions, but then in the framework of GPDs. So, yeah.
You're right, yeah.
So do I understand correctly that it's not really a clean measurement of the exclusivity, that you it's not that you can have some accompanying particles in that measurement? I haven't looked into details of the measurement.
This is a preliminary result only, it's no publication. So this was extracted in 2 bins of Z, and the highest Z bin shows a signal.
Okay.
While the lower one does not.
Thanks.
Okay, I think we should thank Caroline again now and move on to the next talk, which is also about spin structure and 3D structure, but I think with a more theoretical focus. So thank you. Can you make that full screen?
Yes, I just want to hide the video panel. Let me see. And also the, okay. Okay.
Yes, that's good. Okay, thank you. I'll give you a 20-minute warning after 20 minutes. Okay.
Okay, thank you.
Okay.
So I will continue the discussion about the spin of the proton and also the three-dimensional nucleon structure, more on the theoretical point of view. And I would like to start by briefly recalling how the idea of spin was introduced first. It was introduced by Goudsmit and Uhlenbeck, as many of you know, and this one was just an idea which was born from to explain empirically the observation of the spectral line of the hydrogen. Actually, the idea of this self-rotating electron was not very clear from the theoretical point of view, but it was very nice to explain the fine structure observed in the spectral line of the hydrogen. So then they were, even if they were not sure about the theory, they were encouraged very much by Ehrenfest, who took the initiative to publish, to set the publication of these results. And the things would have been quite different if instead of Ehrenfest, they would have a different mentor. Because, for example, also this same idea was also coming to Kronig, but it was very much discouraged by Pauli because the theory was not very well understood. And in particular, Pauli ridiculed the whole thing. And then Kronig, even if he had this idea before Goudsmit and Uhlenbeck didn't follow up. And now, after almost 100 years, what did we learn about the spin of the proton? So conceptually, we know very well what is the spin of a particle, but still it's very challenging to understand for a composite particle like the proton where the spin comes from. And we can use different approaches. For example, we can use approaches through some rules, and then we can try to decompose the spin of the nucleon in various parts in terms of contribution from quark and partons and try to relate them to the experimental observables. Or we can use ab initio calculation, for example, like in a lattice QCD calculation. Or what we can do, we can try to infer some information about the spin and the orbital angular momentum by studying the three-dimensional structure of the nucleon. Then we can use some distribution function like GPD, TMD, or Wigner distribution to give a quantitative assessment about the effects of the spin on the proton structure. So starting with the approach of the spin sum rule, we are used to decompose interval contribution from the spin of the quark, spin of the gluon, and also orbital angular momentum contribution from quarks and gluons. So all these different parts are renormalization scale dependent. And when we say the quark carry a certain amount of spin, we always look at the proton at a particular scale, and this statement is scale dependent. And there are also different ways to split the angular momentum. There is not a unique way. And we are looking for a decomposition which has some requirement. Particularly, we want to relate the different parts to some experimental observables. And also, in particular, we would like to have a clear partonic interpretation for each of these different parts. And the two sum rules which are normally used are the G sum rule, the covariance sum rule, and the canonical sum rule introduced by Jaff and Manuel. So in the G sum rule, you have a contribution from the spin of the gluon, a contribution from the spin of the quark, which can be split in terms, the elicity of the quark, which can be split in terms of spin and orbital angular momentum. The nice feature of this sum rule is that each term is gauge invariant. And also the decomposition is frame independent. It holds in the rest frame of the proton, but also in the infinite momentum frames. The same decomposition is true for the helicity, for the z component of the spin, but also for the transverse angular momentum. And both these two contributions, the helicity for the quark and gluon, can be obtained from moments of GPDs. On the other side, in the case of the canonical sum rule, we have 4 different contributions in terms of spin of the quark and gluon. In particular, this delta sigma is the same that you also have in the G sum rule. And then some contribution which comes from the orbital angular momentum. Now these terms are gauge dependent, but still are measurable because they can be related to some operator which are gauge independent, then to some observable, and only in a particular frame, the infinite momentum frame, in a particular gauge, we can have the partonic interpretation in terms of helicity and orbital angular momentum. So for the helicity part, for the quark and gluon, we can have a direct relation to the polarized parton distribution function. For the orbital angular momentum, they can be obtained from twist-3 GPD and also from Wigner distribution. So this orbital angular momentum for the quark is different from the orbital angular momentum you have in the G-sum rule. You can relate them, the relation is this one in terms of this gauge-dependent term, the potential term. And if you now switch this potential contribution to the gluon part of the Jaffe-Manuel sum rule, you recover the helicity of the helicity that you have in the G-sum rule. So what is the status of the spin sum rule? So we know we have this very nice talk by Caroline, and then we know quite well what is the spin contribution of up and down quark. A little bit less well known is for the heavier quarks. But then if you look at the spin contribution of the gluon, we have just a definite range which comes from measurement. And when we make the extrapolation in the full range from 0 to 1, we have a big uncertainty. These are from 2 different parameterization. So then for the spin of the gluon, just because of the limited range which is measured, we have still a big uncertainty, but still we don't know almost anything from the quantitative point of view about the orbital angular momentum for the different flavor for the gluon. So here is this what we know for the spin in comparison with lattice calculation and phenomenology. These are the results from different lattice calculation, and this is the results which are from the phenomenology extraction, in particular from this different parameterization. This is taken from this white paper, which gives a summary of lattice phenomenological results in the larger community. So then you see this for the we have a quite good agreement, consistency between different lattice calculation and phenomenology, in particular for up and down, a little bit less good for strange. But what is nice is that in both cases, from phenomenology, lattice calculation, the uncertainty are quite have comparable size. And also lattice QCD results will provide some useful inputs for global fits of polarized parton distribution function. And I think there will be a talk in the week by Nobu, just giving this some highlight how to incorporate lattice information in fits of polarized parton distribution function. So here is what we expect, the impact of ESC measurement for the quark spin, for the gluon spin, and then in particular you see the big gain in the case of the gluon spin. So then we are constantly improving the knowledge of the contribution of the spin of the nucleon. And what about a direct measurement of the orbital angular momentum? So to have some quantitative information for the orbital angular momentum, we can look at the G-sum rule. In particular, the quark and gluon helicity can be related to these moments of the unpolarized GPD, H and E. In particular, these are twist-2 GPD, and in the they depend also on T in principle, and here for this sum rule, you have to make an extrapolation at T equal to 0. In addition, you have to span the full range of X to calculate the moments, and this sum rule is valid for any value of xi, but in general it's more convenient to take xi equal to 0, because in this case, this distribution is directly related to the unpolarized pattern distribution function. So this is not directly accessible. In particular, extrapolation at t equal to 0 for any xi is not measurable. Then it requires some model information, some model input. And in this sum rule, if you just look at the integral, you cannot interpret it as angular momentum density. But to recover interpretation in terms of density, you have to look at the orbital angular momentum expressed in terms of twist 3 GPD. In this case, you don't have a simple partonic interpretation, but you have the advantage that you can define a gauge invariant covariant orbital angular momentum density. You can interpret this relation in terms of twist 3 GPD as a density, which gives you the amount of orbital angular momentum as a function of the longitudinal momentum fraction x. So what we know from data, so there were still back 2007, 2008, some model-dependent extraction of the elicit of quark and gluon from DVCS data, in particular from Hermes and JLab. And you see this just that you need some model input to make this extraction, and taking different parameterization to model your GPD, you can get quite a different results. But still now we expect that with the JLab 12, there are different proposals to make more precise measurement, and also in the future with ESC, we are looking forward to improve the situation. So another way to access the orbital angular momentum is through Wigner function. This is a model-independent relation, which gives you the orbital angular momentum of quark. The same relation also holds for gluon, in terms of the Wigner distribution for longitudinal polarized proton and unpolarized quark in the longitudinal polarized proton. And this is a very nice expression, because here you have just the classical expression for the orbital angular momentum, position times momentum, which is weighted by this quasi-distribution. And this is just the expression that you use normally also in statistical mechanics when you want to calculate the expectation value of some operator, in this case, the orbital angular momentum. You can rewrite this relation in this way by introducing some average transfer momentum as a function of the position B-perp. And this, as I told you, is a very intuitive definition of orbital angular momentum, even if now you are looking to some distribution where you require to know precisely at the same time position in transfer momentum, then you have to face the Heisenberg uncertainty principle. In this case, you are involving components of position and momentum which are mutually orthogonal. There are no conflicts with the uncertainty principle. If you just look at the integrand as a function of x, then if you do not integrate over x, you just look you take the same expression, you have an interpretation in terms of orbital angular momentum density. And this Wigner function depends on a Wilson line, a gauge link, and depending on the path that you choose for this gauge link, you can recover both the Jaffe-Manner orbital angular momentum or the G orbital angular momentum. So the same equation is also valid for gluon, and also what is nice, this one can be calculated also in lattice QCD. And if I will have time, I will show you also some results for lattice. And here is just an example of a model calculation of which kind of picture you can get using this relation. In particular, here we have the density plot as a function of the transfer coordinate dx and dy, and this arrow just represents the average transfer momentum of the quark. And then you see, for example, here is the situation of the up quark. The length of this vector gives you the amount of transfer momentum, and then the direction is given by the arrow. And then you start to have an orbital quark which orbit in this direction. And here for the down quark, you have, this is just a model calculation, you have error in this direction, we have orbital motion which is anti-clockwise, then you have a change of the orbital motion in this direction. So, and this is just to visualize the way you can visualize a function of the position of the quark inside the proton is orbital motion. So then, depending on this gauge link, you have the G definition of the Jaffe-Manuel definition. In particular, if you use a straight gauge link, you have the G, orbital angular momentum. And if you use a staple gauge link, which can be in the forward time or in the past, in the future or in the past, you have the Jaffe-Manuel orbital angular momentum. So what is nice, independently if you have a future pointing of past pointing the Wilson line, you have the same orbital angular momentum. So this is the gauge link that you expect in a semi-inclusive deep energy scattering, in this one in the Drellian experiment. And the difference between the two, which just depend on the path of the gauge link, can have a nice interpretation. This nice interpretation was given by Matthias. And this is this difference is a measure of the torque which feels the active quark when it leaves the nucleon in a semi-inclusive deep energy scattering. And this one was also measured in lattice. This is a lattice calculation by Michael Engelhardt. And in particular, in what you are doing, you are taking a gauge link which depends from this parameter eta. In particular, in the limit of eta equal to 0, the gauge link reduces this straight line, which is the gauge link that you have in the case of the G orbital angular momentum. And in the limit of eta going to infinity, you are taking the length of the staple gauge link to infinity in the future, in the past, or in the past, to recover the Jaffe-Manuel definition of orbital angular momentum. In addition, in doing the calculation, you have to take into account this regulator, and then in the limit of psi, you have to look at this calculation in the limit of psi going to infinity. And here is the results. Is the orbital angular momentum normalized to the value of the G orbital angular momentum. Then looking now at very large eta and extrapolating at eta plus infinity, you recover the Jaffe-Manuel orbital angular momentum in the case of the gauge link, which is staple line pointing to pointing in the future. And this is the same as you obtain when the gauge link is pointing in the past. So this is the value that you expect from the Jaffe-Manuel normalized to the value of the G orbital angular momentum. And then you see that you have a sizable torque of the quark. The difference between G and Jaffe-Manuel orbital angular momentum is quite sizable. Okay, so this is just from one Wigner-Wigner distribution, but you have all this bunch of Wigner distribution that you can study as a function of the polarization of the quark and the polarization of the nucleon. You have in total 16 independent Wigner distribution, which depend on 5, which are in the 5-dimensional space, where you have 2 dimension for the coordinate and 3 dimension for the momentum, the transverse momentum and the longitudinal momentum. And what is nice is that all of these functions are independent. They carry independent information and then can be used to infer information about the correlation between spin of the quark, orbital angular momentum of the quark, spin of the target, spin of the target. If you take the integral over K-perp, you recover the GPD. Then you have in total 8 GPD, depending always from the quark and nucleon polarization. On the other side, if you integrate over B-perp, you have the transfer momentum dependent part distribution function. And they also are completely independent functions. There are no relation between the two. Then they can all be used to infer independent information about spin and orbital angular momentum. In particular, the functions which are in red vanish if there is no quark orbital angular momentum. And the black distribution are the one which survive in the collinear limit. So from the GPD, how much time do I have?
Well, it's about 1 minute 30 seconds to your 5-minute warning, so 6.5.
So then I will just keep this X-dependent measurement, which was already discussed by Caroline. I want to now pass to the information that we can get from the GPD for the energy momentum tensor. So we have already seen that the GPD allows us to access the orbital the angular momentum. But this is what is just one of the form factor that you can relate. One of the form factor of the energy momentum tensor. So the energy momentum tensor carry information also about the energy density, the momentum density, and also the spatial component can give us information about shear forces and pressures. And all these form factors are related to moments of the GPD. We have seen already the one which is related to the G-sum rule for the angular momentum, but also we have a similar relation for the momentum fraction carried by the parton, and also for this form factor. This form factor is particularly interesting because if you look at the form factor in the coordinate space, you can relate it to some mechanical properties of the nucleon, in particular to pressure and shear forces. And there was first extraction from JLab data about this form factor as a function of T, and these are these pink violet points, which are compared with different model calculation and also lattice calculation. And this form factor these are the data which were used as a function of T with this systematic error to obtain through a Fourier transform this picture for the pressure and the shear force distribution inside the nucleus. This is very recent. It had just appeared a few days ago. So and then here you obtain this typical picture where as a function of R, you have a positive pressure near the core of the nucleon, which means repulsive, which is counterbalanced by the confining pressure at the periphery to give in total a stable object. So this is the analysis. Okay, here you see different bands. In particular, the green bands are from this data with the relative uncertainty, and then from this orange band is what you would expect with new 12 GeV JLab data. There was also other analysis. The same data were also analyzed by Krasimir by using a more flexible parametrization, in particular using neural networks. And also recently there was a new analysis of all the available data of DVCS, and this one will be discussed more in a parallel session on Thursday. And in particular, here is the analysis with the same JLab data, which was done by Krasimir with neural network. And here is the new analysis as a function of mu square of the scale done by the people, by the parton people, And then you see that now in all the model calculation, you find that this D term is negative, and this is related to the stability of the proton. And now using this neural network approach, you find a big uncertainty, which average value which is negative, but with a big uncertainty. So on the other side, from looking at the momentum, at the transfer momentum, we can study transfer momentum dependent distribution. In this case, you have a complete momentum spectrum of the single particle. You can measure the size in the transfer momentum. And now you don't have something similar to the G-sum rule in the case of TMD. You don't have a spin sum rule in terms of TMD, but you can infer different information about the spin and orbital structure from the different GPD. In particular, if you look to the unpolarized case, you have just a monopole distribution in the transfer momentum space. And adding the polarization for the quark for the nucleon, you expect to find some deformation in the momentum distribution, which can take a dipole or quadrupole size. And looking at this deformation in transfer momentum, you can get some information about the orbital momentum and the spin correlation. So the most studied distribution is the unpolarized distribution function. And here is just a sketch about the impact of expected from EIC for this unpolarized TMD, and also the unpolarized fragmentation function. This one will be discussed in a parallel session by Chiara Bissolotti. And here is just the plot as a function of X and Q square of sensitivity coefficient, which measure the correlation between fit parameters which enter in this phenomenological study of unpolarized TMD and fragmentation function and measurable quantity at EIC. And then you see that you can gain very much about new information about the Q-square dependence, then the non-perturbative evaluation, also the width of both the transformator dependent distribution and also the fragmentation function. So then I want to comment briefly about the Sievers function, which was already discussed. This is a nice function because it's directly related to some information about orbital angular momentum. You have a transversely polarized target, then you have a helicity flip at the nucleon level, and an unpolarized quark, which means the same spin in the initial and final state. And then to compensate the mismatch, the flip of the spin of the nucleon, you need to have a transfer of orbital angular momentum. So then there is a non-trivial correlation between the quark orbital momentum and the spin of the nucleon. This is unique in the TMD case because if you look at the GPD in the impact parameter space, you do not have any analog. And also we know that they need to have the gauge link different from 0 to be different, to be not vanishing. And in particular, you expect that the change sign going from Sidis to Drellian. And these are just some very recent results from a global fit to semi-inclusive diplomatic scattering, Drellian, and boson production. And here is the comparison between the KT dependence of the unpolarized TMD and the Sievers function. Then you see that the Sievers function here is a logarithmic scale, and the Sievers function is much smaller than the unpolarized, and also the uncertainty is much bigger. But already from this data, if you try to reconstruct the density plot in the momentum space, you observe a transverse shift in the distribution for up quark and the down quark, and this transverse shift is just a signature of the correlation between orbital angular momentum and spin. And there will be a full section on Tuesday dedicated to the different Sievers extraction and also to the glue and Sievers. And finally, I want to end with the transversity and tensor charge. There was also in this case a very recent paper about the impact of the solid and ESC measurement for the transversity using both proton and helium-3 target. And here is the coverage in blue from ESC and in red from solid for in X and Q square. And you see they are very, very well complementary. In particular, a solid will cover the very high X region with very good precision thanks to the high luminosity which is expected from solid. And here is the impact from this measurement. Then in particular in green we have the impact from solid data, pseudo data. In blue the impact from the ESC pseudo data, and in yellow combining both measurement. And then you see that you will have much better, a big improvement in the precision for the transversity, in particular for the down quark, thanks to the helium-3 data. And here is the impact for the tensor charge, in particular the first moment of H1. In pink is the current phenomenological extraction, which have a big uncertainty. These are the only extraction from the JAM collaboration, which is compatible with the latest data. But now with the new solid and ESC data, you see that you can improve very much the accuracy of this for the tensor charge, reaching now an accuracy which is competitive also with the lattice calculation. And then as it was anticipated by Caroline, there will be many other data from the Hermes, from class 12, from Compass, and also from Rick, discussing in the parallel session. This is just a short summary of what you expect for semi-inclusive difference scattering measurement, Drellian, and also proton-proton collision. And all these different measurements are very important because they are very useful to test the universality of this different distribution function. And to summarize, so the field of spin and three-dimensional structure is continuously advancing and is also part of the project of many experimental projects worldwide, in particular in the USA. And our knowledge of GPD and TMD is increasing, but we are still many challenging questions. And the best hope to try to reconstruct information about angular momentum, in particular the orbital angular momentum, is to try to put together all the information, direct, indirect information, model-inspired information that we can have for all different kind of pattern distribution function, GPD, TMD, linear distribution. So this is the best hope that we can have to really have to reach some quantitative conclusion about the different part of the spin sum rule. And then I just invite you to follow the spin session, the future session, all the other session, because there are many exciting talks which are coming up during this week. Thank you.
Okay, thank you very much again for that one more very comprehensive and interesting talk. I can see a hand up by Nodoka Yamanaka.
Hello. This is a question about the pressure distribution you plotted in yes. Page 19, yes. Yes. So the proton is a stable system. So why do you have positive and negative pressures distributed? It should be zero if the system is stable, right? Sorry, I cannot understand conceptually.
If the stability tells you that if you integrate this R square times the pressure, you have to get it 0. So, and indeed, it's very important to have both negative and positive contribution, which compensate when you take the overall the whole integral over R, you have this compensation between positive and negative contribution, which guarantee that you have a stable object. It's the integral over R of this quantity, which has to be 0.
For example, if you look at the interval between 1 femtometer and 1.2 femtometer, you have a negative pressure, right? So does this mean if you look at only this region, this place is decaying or collapsing? Sorry, I cannot imagine what is happening.
Okay. You have to think like you have a shell in your proton. In each point, there was also a nice paper recently by Jerry Miller explaining this fact that in each place for each R, you have the pressure which is locally equal to 0. You have a compensated effect from outside this shell and inside this shell. So in this one, you can look also, if you take in particular this two-dimensional picture as a function of in the transverse plane, you have a really density interpretation, and then what you expect that locally for each R, you have just some forces which push outwards, which are compensated from forces which push inwards.
Okay.
You can construct the forces on which act on this shell inside of proton, and locally for each R, they should be equal to 0.
Okay, thank you.
Okay.
Thank you.
Okay, the next hand I saw was from Abe.
Yes, Barbara, very nice survey of the theoretical advancements. I have a question about this same plot that you're showing right now. Are lower X data relevant to this, or are the definitions of certain things do not hold at lower X for these kind of interpretation?
So can you repeat the question? I didn't understand. So
are lower X data important? I mean, currently, these are only based on 6 GeV, and there is a projection that looks better with the 12 GeV data. Are there any, would you say that, a thing like EIC would be helpful, or at that lower X, the interpretations may not, or at least some of the things may not be valid for these kind of interpretations?
Okay. Okay. So you expect to, yes, for sure, not just the low X data will be important in general for gluon. This is just for quark. Indeed, in all this analysis, the gluon contribution was not taken into account. And when you want to interpret this function as a pressure, and you have really to take into account also the gluon contribution to have this kind of interpretation. So what is very important is the T dependence. So then you have in reality I mean, what you are fitting to the data is the t dependence of, if you use a dispersion relation representation, you have the real part of the GPD. It's written as an integral of the imaginary part and the function which depends on t. You are just fitting this function which is t dependent. So of course, more accurate data will help for sure, but I would not say that, I mean, just low X data can play a more important role.
Thank you.
Okay. Charlotte?
Yes, hello. Barbara, I also liked your talk very much. Thank you. I have a question about the orbital angular momentum. So for the interpretation, well, the G decomposition, you look at the orbital angular momentum of your quark inside your nucleon. And for Jaffe-Manoir, you have this contribution with, in addition, this effect of the nucleon remnant. Now, at the same time, the G decomposition, in the G decomposition, the orbital angular momentum of the quarks gets some mixture from gluons, whereas the Jaffe-Manoir decomposition doesn't get any mixing from gluons. So I was wondering if there is a relation between these two aspects. So the interpretation of the orbital angular momentum and this mixture of gluons that is present in one and absent in the other decomposition.
What do you mean mixture with gluon? Because I mean, in G, you have just these three pieces.
Yes, and if you write out your operators, you have this delta minus.
Ah, okay, sorry.
IGA.
Okay.
Yes.
Okay. This is okay. Then the question is,
if the fact that you get this mixture in the G decomposition is related to the interpretation of the orbital angular momentum, or if these are two completely separate aspects.
It's okay. You can is related to the what you call orbital angular momentum. The momentum, when you write, for example, when you define the momentum of the quark, you can use, as you know, the normal derivative. This is what happens in the Jaffe-Manoir, or the covariant derivative. Covariant derivative is also contribution from the gluon. So then it's still a moment. You cannot. When you have a gauge theory, like in this case, this is still momentum of the quark, but which is linked to the gluon contribution. It's indeed the difference between the two is sometimes this in one decomposition is attributed to the gluon, for example. So if you look, this is the Jaffe-Manoir, this is the G, and this is the difference between the two. In the case of G, this contribution is put, when you put this contribution together to the orbital angular momentum of Jaffe-Manoir and delta G, you get the G.
Okay, so there is a link.
There is a link, yeah.
Okay, thank you.
And this part, which, so you can shift this part from the quark to the gluon sector to recover the G, the composition, and this part is what was interpreted by Matthias in terms of the torque, that's U, the quark, in a semi-inclusive differential scattering process, the quark feels when it leaves the nucleon. So because of the interaction with the expectator, when the quark leaves the nucleon, it feels a torque, which is due to this final state interaction, and this is attributed to the difference between the two definitions of orbital angular momentum.
Okay, thank you very much.
Okay, thank you. I think that's it then for this session. And Abbe, did you want to demonstrate the gathered town now?
Yes, so there will be a 10-minute demonstration of what this gather town could do. It's not mandatory. If you know how it works, you can go to lunch right now.